Hello, this is Dr. Cynthia First at the University of Utah, and today we're going to talk about designing op-amp systems. Electrical engineering is about what can you do to a voltage. A lot of times we like to add voltages together, we like to add constants to them, we like to multiply them by various values in order to make the circuit do what we want. Let's suppose that we want our output to be a linear combination of a constant and our input voltage like this. This kind of math might look like 2 times V2 plus minus 2 times some kind of voltage, something like this. So how would we design that sort of system? Whenever we are designing systems, we like to break them down into individual components. For example, we wouldn't really want to have to consider the power plant, the breaker box, and all the outlets in your house individually every time we wanted to design a lamp or a fan. We'll take that entire distribution system and we'll model that as a single source voltage with its source resistance. And then we might consider the lamp and the fan in parallel like so, and we design each of them independently. In order to design individual blocks like this independently, there's a very important concept. That concept is input and output resistances. Let's suppose that we have a circuit, any circuit, that's this black box. If we look in, that's going to give us the input resistance, and if we look into the output side, that's going to give us the output resistance. A lot of times in the book and elsewhere, you will see Z. That is impedance as opposed to resistance. It's the complex resistance, so just consider that to be the same as resistance for this case. If we are looking in to either side, that's the same thing as using the Thevenin resistances, and you calculate it in the same way. Now let's consider the basics of input and output resistance. Here is an example of an equivalent circuit that we would be very likely to build. We would have a source right here with its input equivalent connected onto some kind of amplifier circuit driving some sort of load. If we wanted to figure out how these were working, we would consider the input and output impedances of each of our blocks. Here, for example, is our input circuit. Now, even though it's called an input circuit, you notice it doesn't really have an input resistance. It only has an output resistance. The output resistance looking in, what resistance would be here? We would short out our voltage source, and the only resistance there would be Zs. Now let's consider the amplifier circuit. Looking into the amplifier, remember the fact that when we have a op-amp, the input resistance is approximately infinity. It's very, very high. So when we look into an op-amp, Zn is equal to infinity. Let's consider the Zout. Remember that when we have an op-amp, we have an output resistance, Rout, so our Zout is approximately 0. Then let's look into our load. Zn is Zl, like this. So we now have looked at our input and output resistances or impedances for each one of the elements in our circuit. An input impedance is looking into the input, and an output impedance is looking into the output. Now let's go back to our circuit. Let's take a look again at this circuit and decide what our input and output resistances are. Just like in my previous case, the output resistance of the source block is simply Zs. Now let's look at this fan block right here. The input resistance, right there, would be our fan, and the output resistance would also be our fan. Now here's our last load right here, that's the lamp. And looking into the lamp, that gives me an input resistance of our lamp. Okay, now let's consider how we connect circuits that have different input and output resistances. If we wanted to connect circuit number 1, which has its input and output resistances right here, and we wanted to consider circuit 2 with its input and output resistances, let's see what would happen if we hooked them together. Here's an example where I'd just be connecting a source impedance to a load. So if I look in here, the output resistance is Zs, and if I look in here, the input resistance is Zl. Now imagine what would happen if I hooked them together. The output voltage that I might like here would be Vout1. And let's suppose that I wanted to drive this circuit with a source Vs. And I'm going to drive this, maybe a mixer input impedance or something. And I connect them up like this. What does that give me? That's a voltage divider. We know something about voltage dividers. We know that Vout1 is equal to Vs times Zl over Zl plus Zs, because that's a voltage divider. Now, if ZL is small compared to ZS, we're not going to get the voltage that we wanted at all. The only time that we're going to get the voltage that we wanted to be deriving it with is if ZL is very large compared to ZS. So ZL, much greater than ZS, will give us the result that Vout1 is equal to Vs. So this is a really important feature. When we are designing circuits, and I kind of showed it graphically here, if the input resistance of the second circuit is very large, Zn2 is much greater than Zout1, then we can consider these two circuits to be independent. We can design them separately. Any other case we can't do that, and we'd have to analyze the entire circuit together. So we like it very much if the input impedance of a circuit is very high. Now, in the event that that doesn't happen, what we're going to do is put something called a buffer in the circuit. A buffer multiplies the incoming voltage by 1, but it has this magic thing that the input impedance of the buffer is always large, and the output impedance of the buffer is always small. That makes it so that we can always put a buffer in here, and we can always design our blocks separately. So the buffer allows us to design our input equivalent circuit separate from our load equivalent circuit. Now, another word that we often use for this is loading. So loading occurs when ZL is approximately equal to or less than ZS in this case. Loading happens to make it so that the output voltage that we want isn't the same as the output voltage that we input. So loading is a bad thing. Now let's review again, connecting input and output resistances. If I have a large input resistance and I connect it to a small output resistance, I can design my circuit without a buffer. I can individually design circuit 1 and circuit 2 as if they were not interrelated. Any other time, I'd have to analyze the entire circuit. In the event that I didn't have Zn2 much greater than Zout2, what I would do is put a buffer in that case, and that is going to make it so that I always have a large input impedance and a small output impedance. So these are our two design criteria that allow us to design individual elements of a more complex circuit.